Hi, so in this video we are going to continue our discussion of volumes of revolution, but we are looking specifically at the shell method, and this video is going to focus on finding the volumes of solids that have been generated by revolving a region around the y-axis. So let's take a look at such a solid. Let's assume that we started off with our basic function y equals f of x, this blue curve that's drawn here, and we're leaving our formula as generic. Notice that if we look at our rectangle that we would use to compute the area under the curve, outlined here in black, looking at this rectangle here outlined in black, and we revolved our blue curve around the y-axis, that rectangle gets carried around, and you can see this graphic generates a shell. The reason we're calling it a shell is because it's a very thin, hollow cylinder. So taking that and looking at all the different rectangles, you can see we have kind of a rough approximation of our solid that's going to look like almost like a hollow cone for this particular curve. Okay, so let's go through the same idea as what we had done with discs and washers, but instead of computing the volume of those discs and washers, we're going to compute the volume of those shells. So if we split our curve up into these rectangles and then rotate those rectangles, we can approximate the volume of our solid by adding up the volume of these shells. So that's going to be our concept. Let's find the volume of just a generic ith shell. So looking at what one of those shells would look like, remember the shell has thickness of the same thickness of this rectangle here, which is a delta x. And how would we find it? Well, we'd find it by taking away, the difference between xi and xi minus 1. So the thickness is going to depend on how many rectangles you cut it into. And as you know, we're going to end up doing the same thing we've done, which is letting that delta x approach 0. So these shells are going to become infinitely thin. So now tracking what happens with that delta x, it's the thickness of the wall. Now to compute the volume of these shells, I had a little graphic here to demonstrate how we do this geometrically. So imagine these shells as like a toilet paper tube. And someone said, well, I want you to find the volume of the toilet paper tube, but just the cardboard, not the air inside, obviously. So how could we do that quite easily is, well, if we took scissors and we went ahead and cut along this perforation here and unrolled our shell, now we have this very super simple to find rectangular prism. And remember, to find the volume of one of these boxes, you do length times width times height. So super easy, right? And we already know one of the dimensions is going to be the thickness, which is delta x. Okay, so think about what happened. We cut it, we'd unrolled it. The thickness of this is delta x. So then we need to find two more sides, right? We need to find this long length here, and we need to find basically how tall is the shell. Okay, so looking at the shell, it looks like the shell height, that's super easy to find, right? We're going to go back to our original picture, look at the rectangle, and see that the rectangle is as tall as the curve y equals f of x. And since we're working in the variable x, we can go ahead and stick with that. So we know this is going to be, this length here is going to be f. And because we're working with the ith cylinder, I'm going to use an x sub I there. So that's the length there. Okay, now we need the long side. And the long side is the most interesting because it's going to end up being the circumference. So when you cut it and unroll it, you need to know how far around is the circle. So now we need to find the radius of one of these shells, and the biggest thing that people worry about is, okay, am I looking at the inner or outer radius? It's not a washer. We're not finding it that same way. Remember, the thickness of these is approaching 0. So xi and x sub I minus 1 are getting infinitely close, and thus the radius is going to merge to be just the distance of x sub I. It's going to merge to be x sub I. I'm doing this here in blue. So the radius here in blue is going to become this radius here. So the radius is x sub I. So the length here would be 2 pi x sub I. Okay, so then the volume of the ith shell is now pretty simple to find. It's just going to be length times width times height. So the volume would be 2 pi x sub I times f of x sub I times delta x. Okay, that is the volume of just one of these shells. Let's take a look at what would be the approximate volume of our entire solid. So remember, the concept here is we're going to add up all these shells. So using Riemann sum notation, which is hopefully getting pretty familiar at this point, it would be adding up all the different volumes. And we're ranging from 0 for I up until n minus 1, where n is the number of shells. Okay, so in this case, our capital N would be, it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and now to find the volume of our solid exactly, we're going to have the same concept that we've done now in several different videos, right? So the idea is we're going to let the partition have infinitely thin mesh. What that means is we're going to let our delta x go to 0 as n goes to infinity. So as you cut more and more shells, this gets more and more accurate, and the width of each of those shells approaches 0. So as n goes to infinity, delta x will go to 0, and we're going to have the integral 2 pi x times f of x. We're integrating with respect to x. So the delta x goes to 0. And where are we cutting our shells from? Let's take a look at the picture. It looks like the shells are being sliced from A to B. Okay, so our volume of the solid exactly is given by the integral from A to B of 2 pi x times f of x. Okay, now the biggest question, I'm going to zoom out so you guys can see the graphic to kind of illustrate what I'm talking about here. I'll erase this blue line as well. Many students will ask me, why don't we use a disc and washer here? Which is a really good question, because we've already learned one method for doing these, right? And it feels like, well, why can't we just do that all the time? But the answer is that not all solids are lending themselves well to that. Remember, if we were going to do a disc washer rotated around the y-axis, we would need to cut it up the other direction. So instead of having that black rectangle, our rectangles would have to be green. Okay, so when I cut my rectangle, it's probably here in green. It's still probably not obvious as to why this isn't working, because visually, like, yeah, I can slice it up that way. But think about if someone said, okay, now you need to find out what is the height of these rectangles. Okay, so first of all, we'd need to work in terms of delta y. So everything needs to be in terms of y. And looking at this curve, the curve needs to be written in terms of y. But wait a second. It's a function of x. So if we want to put it in terms of y, we need to be able to express it as a function of y, except we can see right away, is it a function of y? No, it's not. Look at this line. It's failing the vertical line test. Like, if you want something to be a function of y, you have to turn your head so that the y-axis becomes like the x-axis, and take a look at this curve from the other way to see, like, is it actually a function of y? The answer is it's not a function of y, okay? It's a function of x. It passes the vertical line test with respect to x, but it doesn't pass it with respect to y. So if I wanted to work with this in terms of all y's, which I would have to do with disc and washer, I would need to be able to express this curve as a function of y. And this curve is not a function of y. So that's going to be how we boil that down most succinctly. This curve is not a function of y. So let's say you had a curve that passed the line test in both directions. So it was a function of x and a function of y. Then you have a problem that lends itself well to being used with either method. This curve, without any more information, we certainly couldn't do this method. So we will just leave it at that. I'm going to clean this graphic up here. Okay, so let's take a look at some specific examples here. For our first example, we're going to go ahead and let R be the region bounded by the graph of f of x equals sine of quantity x squared. the x-axis, the y-axis, and the vertical line x equals root pi over 2. And we're going to find the volume of the solid generated by rotating the region around the y-axis. Okay, again, we're going to focus on just setting up the integral with the assumption that computing these integrals we're looking at basic integrals, and we'll be covering integration techniques in separate videos. Okay, so let's look at this example. We've drawn our curves here. So here is y equals sine of x squared. Did I know what that graph looked like off the top of my head? I'd like to pretend yes, but the honest answer is no. I did not know what this curve looked like. It's not a basic curve. So if you were drawing this region from scratch yourself, this would be a perfect usage of technology, right? We have Wolfram Alpha, we have graphing calculators. This is the kind of thing where we want you to be using those tools. Okay, so we graph y equals sine of x squared, and there's the vertical line, x equals root pi over 2, and our region here in the first quadrant is shaded in red. We are rotating around the y-axis, so I've drawn that little arrow there to remind myself. And again, we see that phenomenon of if I tried to walk down the path of doing this with disc and washer, look what's going to happen. I would have to draw my rectangles, but we don't pass the vertical line test. There's no way for me to rewrite this y equals sine of x squared as a function of y. So even if I tried disc and washer, I'd be hitting a dead end fairly quickly. So shell is truly the only option for us to do for this. So when you do a shell, you draw your rectangle parallel to the axis that you're rotating. So I'm going to say that again. So shell, parallel. They rhyme. Shell, parallel, versus disc, perpendicular. Those are your two choices to do a problem like this. You can either do a shell or a disc, okay? But the perpendicular rectangle wouldn't work for us because we can't really work in terms of y here. So drawing my rectangle, that's going to give me my shell. Here it is. Okay, as I rotate that rectangle around, I will get a shell that looks like this. Okay, what is my thickness? My thickness, looking at what axis the rectangle has thickness on, it's on the x-axis, so it's going to have a delta x thickness. So this side is going to be a delta x. Okay, then we cut and unwrap. Just to visualize, we cut and unwrap. We have a delta x thickness, and then we need the height of the rectangle. It looks like the rectangle is going to line up on this blue curve. All of our rectangles are going to be on the blue curve. So the height is going to be f of x. So f of x in this case is sine of x squared. Since we're doing it for just an arbitrary cylinder, we're going to go ahead and use that subscript of sub I. Sine of x sub I squared. Okay, and I'm checking. I'm making sure these variables match each other. I'm making sure this x matches here. Good, we're working in terms of x, staying consistent there. Now I need the radius of my cylinder. I need to know this radius. So how far away from the axis of rotation is that cylinder is going to be the radius. It looks like it's a distance of x. It's a distance of x away. So this side is going to be 2 pi x sub I. Okay, now we can go ahead and set up the Riemann sum and the integral. And again, I'm being very consistent here in what I'm showing you guys because my focus on these is exclusively understanding the concepts, exclusively the setup, not so much the nuts and bolts of the computation. For these problems, I'm focusing on your understanding of the Riemann sum and how the Riemann sum relates to the integral. So I don't want you guys obsessing about how to integrate these things. I want you obsessing on the geometry, the setup, and the approximate versus the exact. So the Riemann sum is what you would use to approximate this volume. Okay, and the problem didn't ask for it, but I want you guys to be in the habit of setting it up for practice every time. Okay, so our Riemann sum is going to be, we're adding up the volume of each of these shells, 2 pi x sub I times sine of x sub I squared squared, and I should be careful, that parenthesis is supposed to be on the outside of the xi squared. And then delta x, and the I ranges from 0 to n minus 1, where n equals number of. Okay, so now we have our Riemann sum, and what would our exact volume be? As n goes to infinity, delta x goes to 0, and we end up getting the integral of 2 pi x sine of x squared. We're integrating with respect to x, and we look at where are we cutting our rectangles from. Looks like our rectangles would start being cut from here, shading in green, up from here at 0 to root pi over 2. So we go from 0 to root pi over 2. Okay, so just for practice, let's actually integrate this one by hand. Okay, so computing that integral that gives us the exact volume. I'm noticing that I have something pretty cool going on. I see I have a composition of functions. Here is my inner function, x squared. I see a u, and I see a du right here, 2x. I see my du right there. I don't even need to correct this. So I can go ahead and rewrite this, pulling the pi out. I have sine of u. U is x squared. Du is 2x dx. So I can rewrite this as sine of u du. And one thing that gets people here is whether you want to handle the limits of integration in the beginning or the end of the problem, at some point you don't want to mix and match. So if your original problem had x's, you don't want to just copy the 0 and root pi over 2 down because we've changed variables. So if you want to rewrite this integral exclusively in terms of u, which we just did, you need to change your limits of integration. So if my u is x squared, then I'm going to go ahead and plug in those x values. U is going to be root pi over 2 squared, and I shouldn't do u equals, I should just say u limits. So root pi over 2 squared and 0 squared are my new limits. So 0 and pi over 2. Okay, now I can go ahead and compute this integral. The integral of sine is negative cosine. And I'm evaluating this pi over 2 to 0. And don't forget about that pi that we have out front. So we have pi times negative cosine of pi halves plus cosine of 0. And we end up with just pi. Because cosine 0 is 1, and cosine of pi halves is 0. So this is pi times 1, which is just pi. So there is our exact volume of that solid. Okay, and again, I'm not drawing as much emphasis to the computation of the integral. While I will expect my students to be able to integrate certain integrals using our integration techniques, when we are working on applications, I want your main focus to be on the conceptual understanding. So oftentimes I will just ask for the setup. I will not ask for an integral. Like, you can guarantee that in every single one of these problems, I will ask you for the Riemann sum. I will ask you for the integral. I won't always ask you to compute the integral. So as you're learning this and thinking about what's truly important, I don't want you guys focusing on memorizing identities for setup, because that's really not the point of what we're learning. We're trying to understand in depth what integrating does and the mechanisms of it. So focus more on how we worked this problem here and less on just, memorizing an identity blindly. That's one downfall of the Briggs text, in my opinion, is just a little bit of a focus on computation. Okay, so let's do another example. We're going to let R be the region in the first quadrant bounded by f of x equals 2x minus x squared and below by the x-axis over the interval of 0 to 2. And we went ahead and sketched that out. A lot of talk for what that is, but it ends up being this parabola and just looking at the region that's in the first quadrant. We're going to find the volume of the solid of revolution formed by revolving this region around the y-axis. So again, we're revolving around the y-axis, and I want you to remember we're going to use the shell, because once again, if I try to do a rectangle the other way perpendicular to my axis and try and do it with discs and washers, I get a problem. I can't write this parabola as a function of y because it fails the vertical line test. So we got to stick to shells. And when I draw a rectangle and rotate it around the y, it is going to make a shell that looks like this. Vertical shell, we'll call it. What thickness are we working in? This looks like a delta x. So the thickness of the shell is a delta x. Just quick sketches are okay here. They don't need to be works of art, as Bob Ross would say. Okay, so delta x, the thickness, and let's look at how tall the cylinder would be. The cylinder is going to be the height of the rectangle, which looks like it will be a point on our curve, 2x minus x squared. So that's this length. And then how long is it going to be when you unroll it? It'll be the circumference of the shell. So I need to find the radius of the shell that got generated, and it's going to be the distance from my axis to the rectangle. And so it looks like that's going to be just x, however far out, whichever x value. So it'll be 2 pi times the radius of x. If it helps, just label the radius on your shell. Okay, so now when we sit down to do our Riemann sum, we're working with the ith shell here. So be careful with Riemann sums. I definitely have seen students never add in the subscript for a Riemann sum, and it's not really perfectly correct to do it that way because you have to have an index that you're adding across. So if you're setting up a Riemann sum, all your x's here really need i's to indicate that you're working with some x sub I, one of those little partition values. So this is the Riemann sum, which approximates the volume. 2 pi x sub I times 2x sub I minus x sub I squared times delta x. We are adding from 0 to n minus 1, where n equals the number of shells. Okay, so there's our Riemann sum. Let's go ahead and find the exact volume for the solid, and that will be given by an integral, which is the exact. Okay, so what happens to get from a Riemann sum to an integral? We let the number of shells go to infinity. So as n goes to infinity, the width of each of those shells goes to 0, delta x approaches 0, and we get the integral 2 pi x times 2x minus x squared. The delta x goes to 0. We are integrating with respect to x, and the last step is to write the limits for where would you cut the rectangles. It looks like the rectangle slicing would start here at 0, and it would end at the next x-intercept for this parabola, which looks like it would be happening at 2. Okay, again, I'm fairly used to graphing things, so I've graphed probably the same parabola hundreds of times, and I don't really need to spend a lot of thought finding an intercept. You might not be in that position. So if you had to find an intercept by hand, you would set your curve to 0. So you'd set 2x minus x squared equal to 0, and you'd solve it. If you have technology, obviously most calculators have a function to find the intercepts. Wolfram Alpha, GeoGebra, Desmos, all of those classic free online tools will find intercepts for you as well. Okay, so we're going from 0 to 2. And then that is our exact volume. How would I compute this? I would go ahead and probably factor out the 2 pi. And then I'd be working with 2x squared minus x cubed. And we have a simple power rule there to go ahead and finish us off. This would be 2 over 3 x cubed minus 1 over 4 x fourth. And we're evaluating the antiderivative from 2 to 0. And remembering to multiply by the 2 pi once we're done with that. So we get 2 pi times okay, and I don't even need to plug in the 0 because both of those polynomials will go to 0. So it looks like we're getting 16 over 3 minus 4. And 2 pi times that. So this is going to be 2 pi times 4/3, so 8 pi thirds. There we go. Okay, and again, I'm going to highlight my personal areas I want you guys focusing on. I want you guys focusing on all of this here. Okay, the computation is kind of just gravy. So when I'm looking, I'm going to specifically be prompting you for these things. Okay, just be prepared. Some students, if they are not watching videos, they're not necessarily aware of that. They memorize identities. They just kind of don't understand the deep concepts there behind it. And I definitely want us thinking about the concepts as our foremost priority. So in the next video, we're going to go ahead and take a look at shells when we are rotating our region around the x-axis. See you then.